Good afternoon, everyone. So last week we have studied about different equation of states and how to find out the values of different energy properties like enthalpy, entropy, and the Gibbs free energy and the Helmholtz free energy. All these, okay, and these all energy properties are how they are related. That thing we learned in the last week, where we were relating this U, H, A, and G using the UHAG rule and fundamental property relations were there. So last week we learned the equation of states where these properties are again related to the pressure, volume, and temperature, these things. So we learned different equation of states like the van der Waals, the Penck-Robinson, the Redlich-Kwong, and Redlich-Kwong like these, and how and they are expressed and what are the different things expressed in terms of temperature and pressure. And we also introduced the term the reduced temperature, reduced pressure. So these are defined based on the critical temperature and critical pressure of a pure substance. So let me share my screen. So, okay. So today we are coming to the sixth week of the NPTEL course Chemical Engineering Thermodynamics by Professor Shashidhar Kumar from IIT Tirupati in Department of Chemical Engineering. And I'm Namrata Kulkarni, a PMR scholar from IIT Madras in Department of Chemical Engineering. So this is what I was telling you all that yeah. So this is a general cubic equation of state where we are written P, R, T, and V. And we have talked about what does this A account for and what does B account for. So A accounts for the molecular interactions and B is for taking account the finite size of the molecules also, which is very small compared to the capital V. And these are expressed in terms of omega, psi, alpha, these few functions for different equation of states. So these things I have forgotten last week that it can be transformed into this way where we'll get a cubic equation in terms of Z. This is the compressibility factor. So we can find three roots here based on this beta and Q. Okay, so coming to today, so we have these energy property relations and okay, coming to this thing that we know that G or G by RT, these are the things to tell us about the process. Yeah, a feasibility. Delta G negative is visible, delta S positive is feasible. So that is what tells us about different processes. And now we are expressing this instead of G, we are taking the variable G by RT. So differential of that, and this is the total differential, and we define it once with the constant temperature and once more with constant G. So it is expressed like this. So now we know this dG is expressed as in terms of dP and dt for a closed system like this. On substituting this here, we get 1 by RT of VdP. Actually, there is a lag in voice and this written annotation in my case. So excuse me for that. I don't know why this is happening. So VdP minus SdP. minus G. G again is H minus Ts by RT square into dt. So cancelling the terms here for the ST, we finally get this A by RT dt minus H by RT square dt. Here you can see, okay, we can express one thing here, which is V by RT equals to rho of G by RT with respect to rho P. So at constant temperature. This is one thing. And we also have H by RT equals to minus P into rho G by RT by rho E at constant pressure. So we have these both equations are used very frequently for the derivations. So I want please keep note of these things, V by RT and H by RT. Similarly, this is covering the G, V, H, and S, and U can also be expressed in a similar way, where S by R is H by RT minus G by RT. Right, we know this, right? G is equal to H minus Ts. So from that we get this, and U H is equal to U plus V. So from that we get this relation. And when you put these values here, we are getting relations for G, V, H, S, and Q. All property information is understood here. But the thing is, this G or G by RT are not measurable through any experiments. Okay, right? So we don't know what is dou G by dou G by RT with the pressure, with respect to temperature, or whatever. We don't know. So we are trying to, we are defining a new thing, which is residual property, which is defined as M minus MIG. Means this is telling us the deviation from the ideality. Okay, and or else we can express this as M is equal to MIG plus MR, where we define this calculation for ideal gas, and then we account whatever is there for the real system. So accounts the volume and interactions. This residual thing accounts for all that, and which is actually the difference between the ideal thing and the real system. Right. So this is defined for extensive thermodynamic properties, molar value of that. Here, these 5 are the extensive molar properties. Right. So I will be defining for the G here. So GR is equal to G minus GIG for the ideal gas at the event T and P. Right? And we know earlier what we had the relation, which is V by RT is equal to okay, dou R G by RT with respect to dou P at constant temperature. Right? So if I take the same thing for the residual thing, which is actually minus Ig only. So if I express it as GR by RT equals to 0 to P, VR by RT dp. This is the integrand of this plus g ig by rt at p tends to 0. So that is when the ideal gas is defined, right? In the last session, we have discussed that when p tends to 0, it is going to be an ideal gas behavior. So if you express this as some j equals to j plus, so v by rt we can define as, so generally z is equal to v by rt. Similarly, zr, so that zig, okay, zig is one only, right? So actual z is vv by rt. Right, we have v by rt. So plus 1. So have it here as uh, z minus 1 dp by p from 0 to p. Okay. This is defined as constant temperature because we are taking this equation. That's why, right? And so similarly, we will be writing for HR by RT equals to minus T 0 to P. So already we know what is GR by RT. So we are differentiating on that and then integrating. So we get dou Z by dou T at constant P. We are differentiating with respect to temperature. So that's why we have this dou Z by dou T. And then again we have this differentiation is at constant pressure. So that's why this one. And then again dP by T. Okay, right? And this is also defined at constant temperature. Or else you can derive this using the Leibniz law. So, and similarly, we have the relation, right? SR by R is equal to HR by RT minus GR by RT. So now we have SR, HR and GR by RT also. You based on the relation of Z, right? Here we have based on GR by RT is equal to J plus Z minus 1 dP by P. And here also dou Z by dou P constant P into dP by T. At the constant temperature, we have all these things. So this one and all these are defined at constant temperature. So these are the findings which can be used for finding the GVH index and the residual properties. So one thing has to be noted here is this J, and so this integral will have minus something, which is at p tends to p is equal to 0. And G is all this J is also when p is 0. So this also is a relation for G by RT, right? What I'm saying is this term and the third term will get cancelled, and what you will be having is at the pressure E only. So now coming to a few questions. Given that molar residual Gibbs free energy GR and molar residual volume are related as this, which we have recently did it here, and at a P is equal to 0.2 megapascal. So we have P is equal to 0.2 into 10 power 6 Pascal. The gas may be assumed to follow the virial equation state Z is equal to 1 plus pprt, where B is this. So what is the value of GR? So what we have here already is GR by RT equals to 0 to P, PR by RT into dP. Upon the substitution, we get 0 to P Z minus 1 dP by T. And this here Z minus 1 plus Pp by RT, right? So 0 to P. Once the P gets cancelled, we get B by RT into dP. Equals to Pp by RT. So it implies GR is Pp. Find this RT, it's cancelled. So at a pressure T is equal to point this. So we get minus 10 power minus 4 meter cube per mole into 0.2 into 10 power 6 Pascal. So which gives us minus 20 Pascal into meter cube. So this is Newton per meter square, right? Pressure unit. So we get Newton meter. Newton meter is generally work, which is expressed as joule. So joule per mole. Right? I think it's clear now. So we have a relation for Z, and that's how we have found GR by RT. Now, using this GR, we can get HR and we can get SR. So this HR is obtained from dou Z by dou Z by dou T. So that relation. So we'll be working on that also. We can get the VR also here, which is RT by Z minus 1. So again, Z minus 1 is PP by RT. So, okay, coming to the next question. Your gas or base that is equal to 1 plus PP by RT. The value of P is this much. the residual molar enthalpy of the gas at 1000 kilopascal and 300 Kelvin is what? So P and T are given and we have to find the HR. So what we have is HR by RT equals to minus T rho of GR by RT by rho T at constant pressure. So this is expressed again as, so what is GR by RT which we have found earlier? This we have found GR by RT is Vp by RT. So using the same here, minus P into dou of Vp by RT with respect to T at constant P. So this is minus T into Bp by R into minus 1 by T square, right? So this is Bp by RT again. This is HR by RT. So we have HR is equal to Bp. Now at this temperature and pressure, we have HR equals to 10 power minus 4 meter cube per mole into pressure is 10 power 3 into again kilopascal, so 10 power 6 Pascal. So this gives us 10 power 2 joule per mole, right? Okay. So earlier I didn't explain about the generalized correlation. So all these things have been clearly explained by Kumar sir in video lectures. Where here Z is expressed as Z0 plus omega into Z1. This is called as eccentric factor. And the Z0 and Z1 are expressed, are already known as TR and PR from Lee Kessler tables. So what is TR is expressed as PR is equal to P by TC and PR is P by PPC. Right? Now using these things, it is explained by professor also that HR by RTC is that not and H0 and H1 the same. Similarly for the entropy also. So this thing can be actually extended to gas mixtures. So theoretically, this extension is not valid or not explained properly, but these are just approximations which can be made for gas mixtures only. So where we write like omega, which acts as eccentric factor, is summation of yi into omega I. Here this is the mole fraction of gas I or species I. Okay. So also it can be done PC similarly. Okay. IITC I. So this is expecting PC. And similarly for PPC. Okay. So using these things, we go for estimate V, HR, and SR for an equimolar mixture of carbon dioxide and propane at 450 Kelvin and 140 bar by the Lee-Kessler correlations. So coming to the firstly we will consider about CO2 and propane. So from the appendix of any book, generally you can find the critical temperatures and critical pressures for these common gases. So what we have here is 304.2 Kelvin. This is 369.8 Kelvin. And here 73.83 Kelvin. This is 42.48. Sorry, this bar. Okay. Bar. And omega is 0.224 and it is 0.152. So using these, by using the above relations, we get omega is equal to, so here equimolar mixture is there, so 0.5 into summation. Okay, and we get it as 0.188. Similarly, we get TPC is equal to 337 Kelvin. And PPC equals to 58.15 bar. So I don't see many participants here. So that's why I'm not doing any practice here. So I am noting down whatever calculations I have done, but it will be very good that if when you are listening to this session, please go through the calculations, because generally in competitive exams or in the final exam of this NPTEL course also, you have to go through calculations and you have to get used to them. So please do the calculations and follow the methodology properly. The thinking for what to calculate first, not getting puzzled, okay? Please go through them, then you will understand it very clearly. So what we have already here is temperature is 450 Kelvin. So now we have DR is equal to 450 by this 337. Okay, 337 Kelvin. So the ratio will be 1.335. Okay. And similarly, PR will be 140 bar by 58.515, which gives us 2.41. So now we want to estimate the V. So V, how can we get generally? V is equal to ZRT by T. So we don't know what is the value of Z. So Z can be calculated as Z is equal to Z naught plus omega Z1. So coming to how to find Z naught and Z1, I'll be explaining in a few minutes. Okay. And one more thing, how to find HR and SR. So we have HR by RT relation for this. Okay. Naught plus HR by RT 1 into omega is equal to HR by RT. Similarly for SR. So these things can be found at a given PR and PR in the Lee-Kessler tables. So I will be going through the latest tables for a minute. So this I'm showing you from the Smith and Vannes book. The appendix D contains the generalized correlations. Um, so the Z naught and we have Z1. So now what we have here is TR, value of TR is 1.3, okay, and PR is 2.51. So you can see here this table D.1 is for the range of PR from 0.01 to 1 only. And we have PR is 2.41. So I'm going to table D.3, which is in the range of 1 to 10. Okay. So now I want to know where 2.4 is. Okay. Right. So in between this, so I need to do interpolation, right? And that PR is value 1.3. So here I have 1.1, 1.3. Okay, 1.33 I have, but I think I can make, based on the how much variation I'm seeing, I can approximate it. Okay, so I have 2.4. So 2 and 3, how much difference? And 1.3, 0.69, 0.63. So I must do interpolation between these. Okay. And also I'm 1.3, 1.4, it is 0.69. This is 0.77. Okay. So I'll show you for Z naught how to do the interpolation and finding the value in between. So what we have here, this 2 is here, 3, 1.3 and 1.5. In this line, I have 0.69 and 0.77. What I want is at 1.33. So at 1.3, I have 0.69. 1.33, how much? And 1.4, I have 0.77. So first I find the slope. This is, for example, y value and this is the x value. Okay. And we want to know the y value in between this. 1 minute. I'll show you on a whiteboard instead of using this. So I'll explain here. Right? So we have at 1.3, I have the value of 0.69. At 1.4, I have the value of 0.77. So my slope is 0.77 minus 0.69 by 1.4 minus 1.3. So we'll have this slope. Okay. So now equation I have is y is equal to mx plus c. Or else you can write this as y minus y naught is equal to m of x minus x naught. Okay, so in between, if there is 1.33, right? So what is the value of y here in between these? So slope in between these the same as the slope in between these two. Okay. Same slope is contained. Or this one you can derive from this also y is equal to mx plus c. So you will subtract two different the equation at two different points. So you will use this. You will equate this to y, which is unknown, minus y naught, which is 0.69 by x. X is 1.33, right? So 1.33 minus x naught is 1.3. So the slope is 0.8. I will do y is equal to 0.69 plus 0.8 into 0.3. Sorry, this is 0.03. So you will have 0.714. So this is the value of z naught at TR is equal to 1.33 and CR is equal to 2. And similarly, we will find Z naught at TR is equal to 1.33, but at PR is equal to what? Hmm. 3. So, how will you approximate? So, at PR is equal to 2, you will have a Z naught. And PR is equal to 3, you will have a Z naught. Right? What do you want to know is PR is equal to 2.4. What is the Z naught? So, the way we have found here, similarly, you will find the Y here, which is the correct value of Z naught and that TR and that PR. So if there is so much difference only, this value is going to change so much. If it is not there, you can take approximation here, right? So similarly, you have to do for the Z1 also. So now this Z naught, you will get it as 0.697. Okay. And similarly, Z1 you will get as 0.205. So on doing that, we will be getting Z naught plus omega Z1. Here's omega, we have already found 180 omega Z1, which will be giving us 0.736. So we should know that this should be always less than 1. So Z is equal to 1 as ideal gas. Right? So this should be always less than 1. So you will have V by RT, right? So V is equal to delta RT by P. And this way you will find 6.7 centimeter cube per mole. So I'm telling you people how to undo the problem instead of focusing on the calculations. Okay, for this I can give you an information that R is 0.08314 in the units of liter bar per mole Kelvin. Okay, and this liter is expressed in terms of centimeter cube as 1 liter equals to 10 power 3 centimeter cube. Okay, and similarly you have to do for the H0 and H1, where now I'll be showing you about yeah. So I think I'm not sharing the screen here, right? So so this one. So this was for the Z naught, Z1, and this again for HR naught by RTC. Okay. So again, you have to find the HR value again, you should multiply it with the TC here. So TC which we have found here is somewhat around 337 Kelvin. So you should be multiplying with that and the R value also according to that in 0.314 that we have, right? So you can refer to this textbook which is available freely on the internet. right? So any like small part of the whole question can be asked in generally competitive exams uh, in anywhere. Okay, so if you're preparing on the point of examination, that is fine. But if you are thinking in a point of like learning the thermodynamics, so that is the thing. So what you have learned from this session is like how this is extended to the gas mixtures. So even if you don't know what is the equation of state followed by a system, we don't need to worry, and we have Lee-Casper correlations where we just find out the reduced pressure and reduced temperature. So what is the worry? Like if you know the equation of state, that is more accurate, and Lee-Casper thing is somewhat lesser accurate, or like this accuracy thing you have to find out. So here we are doing only based on for normal system. We are just taking an instance and trying to understand the concept more well. But if you go for actual industrial applications, then there comes the matter. So just a small system, temperature fluctuations will be here and there. So you don't know what to follow, right? So what is the like if I say, see this system has a volume of some 1 liter at this temperature. Okay, I can't build a reactor of just 1 liter. How much more should I build a reactor? For example, should I take 2 liters of reactor? So I'm saying in very small quantities, liters. If it comes to like uh, 1,000 liters, right? So if I increase the temperature, if the temperature goes above this, okay, some reaction is happening inside, then how much volume may increase? This, if you can't apply the ideal gas thing for every system, right? For that type of liquids, what type of equation of system is followed, and how much deviation from ideality is there, you should account that. And if I increase this much temperature, how much will be the volume? So how much like what empty space should I keep it there for the safety purpose? So it plays a very big role in real systems, in real problems, right? So all these problems are just uh, to understand the concept, applying the equations, that's all. But if you really go to the real applications, the significance of all these things are absurd. So I hope you people are doing well with this course. Almost half of the course is done, but the real taste, the real essence of the course is going to come now for the solution thermodynamics and gas mixtures and all. So have a, be enthusiastic towards learning this course. Thank you. Thank you for today's. Yeah, thank you.